All right, so this lecture is going to cover confidence intervals when we're dealing with two populations and we have independent samples. So let's jump right into the process or the procedure for calculating these confidence intervals. All right, first thing we're going to look at are the assumptions. Here we have the random sample being an assumption again, and we're assuming that this is a random sample with from a normal population with the mean mu1 and a standard deviation sigma. And notice again, this sigma does not have a subscript. And just like in the last lecture, the fact that this doesn't have a subscript means that we're assuming that those population standard deviations are equal. And again, that assumption has a name. It's called homoscedasticity, but that's the idea. And it isn't always talked about in a lot of detail in stats classes, but it is an assumption for pooling the standard deviation, which is the method that we use to combine those two sample standard deviations together into one value. So both samples are random samples. That's an assumption. Both populations are also normal populations. And again, the normality assumption is not as crucial if the sample sizes are large, and preferably even the same. And this is again because the t statistic is a robust statistic. All right. So then we have some data. And what we're going to do is calculate the sample means for those data sets and the sample standard deviations. So notice we have the estimate for the difference. So this is complicated, but x bar sub 1 is an estimate of mu1. X bar sub 2 is an estimate of mu2. So x bar sub 1 minus x bar sub 2 is an estimate of the difference in the population means, or mu1 minus mu2. So we could find confidence intervals for any three of these population means. And in this example, we're looking at a confidence interval for the difference in population means. So we use the difference in sample means for our point estimate. So you can go back and think about the BB fly swatter example that I talked about. Same kind of thing. We're trying to estimate the difference in population means. We're going to use the difference in sample means as our estimate. Plus or minus t star, an appropriate percentile of the appropriate t distribution. I'll talk more about this percentile later on. Now what this is going to tell us, the t star, is this is the number of standard errors. The standard errors is one way to think about standard deviation. It's the adjusted standard deviation, or the one that's been adjusted using the central limit theorem. In any case, t star is how many of these things that we're going to use to create the interval, and then this quantity is the standard error, and it's the standard error for this, the difference in sample means. So all of this, again, is very complicated. And then we have the pooling issue, and what we call the pooled standard deviation is found by taking a weighted average of the variances and then taking the square root of that. So in a sense, the pooled standard deviation is like the average of the two standard deviations from the two samples. Because again, we need to boil these values down into single numbers. how do we interpret the interval? Well, the interval gives potential values for the difference in the population means based on independent random samples, one from each population. The interval may be used to test hypotheses when the alternative hypothesis is two-sided. We'll talk about that in a little bit too. The confidence level pertains to the proportion of times the procedure produces an interval that actually contains mu1 minus mu2 when this procedure is repeated over and over using new independent random samples of the same size. Okay, so let's talk final exam here for a minute. This paragraph is the frequentist. Interpretation. I usually ask on the final exam to give a short essay or a short answer on what is the frequentist interpretation. So this is a really great paragraph that pertains to the frequentist interpretation. This is the simulation stuff that we've done simulations or I've done simulations, and we have an activity on these simulations to look at this frequentist interpretation. So the confidence level is the proportion of times. So 95% confidence means 95 times out of 100, the procedure produces an interval that actually contains the true difference in the population means. When the procedure is repeated over and over using new independent random samples, each of the same size. Okay, all right. Let's take a look at an example. A business manager of a local health clinic is interested in estimating the differences in the fees for extended office visits for her clinic and the fees for extended office visits at newly opened group practice, and then they're coded office is 1, and then we have office 1 and office 2. So she obtained data on the fees for 15 visits from her clinic and for 15 visits from the group practice, recorded in dollars. Assume that the fees at each office are values of independent random samples where the two distributions are approximately normally distributed with equal population standard deviation. So that gets back to this assumption to pool the standard deviations. We have to have this be true. So therefore, that means by stating that so explicitly in the problem, it means we must pool, or the answer in the back of the book, if there were one, would be to pool the standard deviation. And technically, the right answer would be to pool the standard deviations. Anyway, all right. So what we're going to do is calculate a confidence interval for the difference in those true means. All right. And so let's talk about the general form of this confidence interval for a minute. Okay, so we have our point estimate, all right? Now, in this case, the point estimate is a point estimate for mu1 minus mu2. So our point estimate for that difference is x bar 1 minus x bar 2. Then we're going to create the interval by adding and subtracting a few, T star tells us how many, standard errors. So then we have this formula for the standard error. And that's the general pattern here. Pooled standard deviation is given by the square root of n1 minus 1, sample variance 1, plus n2 minus 1 times the sample variance for sample 2, divided by n1 plus n2 minus 1. So let's do the calculation. I'll start with the pooled standard deviation for this example. So both samples are of size 15. So 15 minus 1 is 14. And the first standard deviation was 3.248. And then the sample size for the second sample was also 15. So 15 minus 1 is 14. The other standard deviation was 2.915. And the whole thing is going to get divided by 15 plus 15 minus 2. Now, if you do the calculation, what you end up with is about 12.3265. So that's the pooled standard deviation. So when I go to calculate the actual interval, what I would do is replace x bar sub 1 with 20.867, which was the sample mean for the first clinic, minus 19.067, which is the sample mean for the second clinic, plus or minus. Now I got an issue here. I got to figure out what this t star value is, but I've calculated the pooled standard deviation, so I know that I'm going to take 12, this is going to have 12.3265, that's the pooled standard deviation, and then the whole thing's going to be multiplied by 1 over 15 plus 1 over 15. So I still have this issue of what to put here in the parentheses for t star. So let's talk about that for a second. Off to the side here, I will draw, or attempt to draw, a t distribution. So this would be the t distribution with 28 degrees of freedom. And let's see, it's going to be centered at 0. T is the variable. We put some values on the axis for scaling. Okay, so here's the idea. I need to know what, say I want to create a 95% confidence interval here. So the question is, what t star value, here we're going to have negative t star on the other side. So what's the t star value that bounds 95% area under the T28 distribution? That's the question. And the way what the book calls T star is the percentile. Corresponding to the level of confidence. All right, so what does that mean? Well, okay, percentile. That means the percentile is the proportion of the population, in this case, that is below T star. So what percentile is that? Well, what we have to realize here is that if we have 95% of the area between negative T star and T star, that leaves 5% to be split equally between the two tails. So that means we have 2.5% plus 95%. So T star in this case, T star is the 97.5th percentile. So how do we calculate that? Well, there's an option. I'm not going to go through all the details. I just want to kind of thumbnail sketch this out so you have some idea what this T star value is and where it comes from. But if you go to the second or if you go to the second vars key under the distribution menu, what you'll find is something called inverse T. Enter the percentile on the calculator for the T distribution with 28 degrees of freedom, and what you'll get back is about 2.0484. And so that's the number that goes right here in these parentheses. So, do the arithmetic. By the way, this quantity right here is what we call the margin of error. And this is the point estimate for the difference. Oops, I forgot this part though. Don't want to forget that. So when I do this calculation, I get negative 7.41 and an upper limit of 11.02. So what could we say about a hypothesis like this? Well, excuse me, notice that 0 is a member of or is in this confidence interval. So since I'm doing a two-tailed test, notice that in a sense what I'm really talking about is an alpha. We could interpret this for an alpha of 5%. In other words, the idea here is that 0 is one of our possible estimates for the difference in means. So since 95% of the time, that true difference will be in this interval. Now, I won't have the same limits. It'll be different, 100 different intervals calculated from 100 different samples with the analysis all done this way. It means 95 of them will capture the true mean. So we're 95% confident that the true mean could be 0. That means we would reject the null based on those assumptions 5% of the time. So this confidence interval would not be evidence that there was any significant difference in the fees. And the reason is because the hypothesized difference is one of the possible estimates in the interval. All right, here's another example. So we have a researcher who's interested in comparing body weights for 2 strains of laboratory mice. She observed the following weights in grams of adult mice. researcher was interested in seeing whether these data provide evidence of a difference in mean body weight of the two strains. And we're asked to observe that the data, or we're asked to assume that the data are observed values of independent random samples. And two distributions are normal with common population standard deviation. So there's the pooling concept coming up again. So let's enter this data into the calculator. And I think, again, I'll use L1 and L2. And we have strain 1 and we have strain 2. So I'm clearing out the data that was in there in the last example. So we have 32, 35, 36, 37, 38, 41, and 43. And in L2, I'm going to put 38, 39, 39, 40, 44, 46, 47, and 47. Oh, not 17. Okay. Now, as with many of the other statistical processes, this one's built into the calculator as well. So if you go to Stat, you go to Tests, you scroll down a little bit, you will find two-sample t-interval. Again, we have data. Strain 1 is in L1. So I'm going to leave the cursor on data, and I'm going to put L1 in list 1, L2 in list 2. Confidence level. Let's do this at 95%. Again, we can choose whatever confidence level we wish. Pool standard deviation. The answer here is yes, because we're told in the problem that the two distributions are normal and they have common population standard deviations. That means pooling is legitimate. I'm going to calculate the interval, and what we end up with is the following confidence interval. So we're going to estimate the mean difference in the body weights to be somewhere between negative 9.32 and negative 0.8227. Now again, we can talk about this in terms of a hypothesis test. And notice this time, this time 0 is not on the interval. So 0 is not one of the estimated differences. Therefore, in a two-tailed test, this confidence interval would be evidence, statistically significant evidence, that H naught should be rejected. So what we can conclude is that based on this confidence interval, there's statistically significant evidence that the difference in the mean body weights is less than 0. And ultimately what that means is strain 2 we have statistical evidence that strain 2 is heavier than strain 1. And again, I go out on a little bit of a limb here, perhaps because the idea with the two-tailed test is the fact that really the level of confidence, the 95% confidence, is coming from the fact that we're looking at T star values for whatever the particular T distribution is. Again, we're at 95% here. So our T star values are based on that 95% level of confidence. So there's a so we have to think about it's. So when we're talking about alpha here of being 5%, it's really split between these two tails. So the alpha of 5% is based on a 5% is based on a two-tailed test. But the fact that the T or the interval is negative, or all the values in the interval are negative values, it does indicate that mu1 is smaller than mu2. But again, we could do a straight hypothesis test if our real question is, if our question were different. Notice here we're estimating the difference in means, but if our question were, are strain 2 mice on average heavier than strain 1, we would just do a hypothesis test. I want to go through some notes about the assumptions behind the processes that we've been using. So the two independent samples pooled t-test is a very powerful technique for comparing the means of two populations, provided the assumptions hold. And now we're going to talk about what happens if some of the assumptions are not satisfied. For example, if the sample sizes are large enough to apply the central limit theorem, then the assumption of the normal population is less crucial, since the distribution of the difference in sample means will be approximately normal. Also, if the sample sizes are equal, the assumption of common population standard deviations is not so crucial. Okay, so if the sample sizes are the same, then this homoscedasticity assumption is not that crucial either. And the t-test statistic will still follow a t-distribution. If the population standard deviations were known and not necessarily equal, we could base our test statistic on this particular formula. This is a very simple approach and not very practical really, but if the sample sizes are large, the normal approximation for this test statistic remains valid. The fact that the Z statistic or test statistic we're talking about is standard normal, that assumption is still valid even if the population standard deviations are estimated by the sample standard deviations. So again, if you think all the way back to when we were talking about Z and T distributions, the idea here is that Z and T are going to give basically the same proportions when you get up to a certain degree of freedom. So again, you're not really going to gain that much by possibly, or I should say the differences in the results aren't going to be that different when you have a large sample size. Now, if the population standard deviations are not known and not assumed to be equal, then we have another test statistic that we use. So this is the example where we would not pool the standard deviation. So if you notice, we go back to this particular Z transformation, you notice the form of this Z transformation is very similar to the form of this T transformation. And really all that's changed is S sigma 1 and sigma 2 have been replaced by S1 and S2. Now the problem is though the sampling distribution of this variable is not a t-distribution, and it's complicated. And I'm not going to even talk about this anymore, but I just wanted to put this out there to raise your awareness that pooling the standard deviation isn't always possible or justifiable, and that there's and again, one of the points I want to make is that as these assumptions become no longer reasonable, life gets more complicated. But computer software does this for us. This very complicated degree of freedom formula and the transformation are already dealt with by the calculator. If you go back to the calculator for a minute and if we were to redo this last calculation we did, I'm just going to redo the last one. We could have redone any of them, because what I want to demonstrate to you, is this the right one? Two sample t interval. All right. Is the calculator gives us a choice, pool yes or pool no. So again, this is very typical of how technology works. So if it were not reasonable to assume that those populations had equal standard deviations, sometimes we just say equal variances, then I would just check no here, and I would get a slightly different confidence interval. Negative 9.308 and negative for a lower limit, and negative 3.353. So again, real close to what I got in this original one. So what we really need to be able to do is understand the assumptions and understand which particular version of the statistical process is most appropriate for the context. So memorizing all these formulas is really kind of a waste of time, in my opinion. What you want to do is focus on and memorize which particular tests go with which particular assumptions. So that's where I think your focus should be, and that's how those are the types of things that I'll be asking you about primarily on the final exam. Okay, well, anyway, let's see. I think that's the end of this lecture, so see you next time.